This is Chapter 6, Ionic and Molecular Compounds, and we're going into Section 6, Lewis Structures for Molecules and Polyatomic Ions. We learned that covalent compounds form through the sharing of electrons between different atoms of different elements, and now we're going to look at a way that we can actually depict this sharing using what's known as a Lewis structure, or a Lewis diagram. We encountered this a little bit already when we looked at periodic trends and the valence electrons around atoms, and we saw that you can draw a specific Lewis symbol for each element, and that shows the chemical symbol and a dot for each one of its valence electrons. So the Lewis structure for a molecule is going to incorporate the Lewis symbols for the individual atoms and fit them together to give a picture of how the electrons are shared in the molecule. In order to draw a Lewis diagram for a molecule, we need a little bit of a better understanding of how covalent bonds form and how covalent molecules form. So to get that understanding, we're going to take a step back and look at the formation of one of the simplest molecules, which is the hydrogen molecule. So hydrogen atoms typically are not stable on their own. Okay, a single hydrogen atom is not very stable by itself under normal conditions. But two hydrogen atoms can join together to form what's called a hydrogen molecule or hydrogen gas. When you hear the term hydrogen gas, they're really referring to a gas where each particle is made up of two hydrogen atoms stuck together. Sometimes it's called dihydrogen, but more commonly it's just referred to as hydrogen gas. Okay? So here we can see two hydrogen atoms with the protons in red and the electrons in blue. And the sort of red cloud around the protons is to indicate the orbital, the 1s orbital that the electron is in a hydrogen atom. Okay? So a hydrogen atom, it's atomic number 1, so it has one proton in its nucleus, and to balance out that charge, it's orbited by one electron. Okay? For this purpose, we don't need to worry about the neutrons at all. It doesn't affect anything. So one proton surrounded by one electron is a hydrogen atom. Here we have two hydrogen atoms. They're far apart. They don't really care about each other. They're not really attracted to each other. They each have their own electron. But when the atoms start to come closer together, the electrons from both atoms become attracted to both nuclei, right? The electrons are negative, the nuclei are positive. So the electrons from one hydrogen atom can begin to feel the pull from the nucleus of another hydrogen atom, okay? So far, they're just close together and they're feeling that pull a little bit, but they haven't formed a molecule yet, okay? There's still two distinct circles, two distinct orbitals on separate atoms. But if we push them together a little bit more, those two distinct orbitals on the separate atoms can actually begin to blend together, okay? And then you can have the two electrons, one from each atom, go into that new orbital that's been formed from the blending of the two old orbitals, and now that orbital will be filled, right? An orbital can hold up to two electrons. We learned that in the previous chapters. So now we have a filled orbital with two electrons in it, one spin up and one spin down. Okay, so now the electrons are paired together. And this is a configuration that's similar to helium, right? Helium is a noble gas because it has a 1s orbital that has two electrons in it. It's a filled orbital in a filled energy level. Okay? So this is similar to that. The hydrogen molecule has an electron configuration somewhat similar to helium. So this shared pair of electrons, right? Because now these electrons are both orbiting both nuclei, so we can't really say that they belong to one or the other. They're shared between them. And this shared pair of electrons is called a covalent bond. Okay? Again, it's covalent because they're part of both valence shells from both atoms. Okay? So the valences sort of blend together. And this arrangement, as I said, is more stable than individual hydrogen atoms. So this has become a new stable unit, which we call the hydrogen molecule, or the H2 molecule. In your book, you can see this chart, which shows you how the energy of the system decreases as the distance between the nuclei decreases, right? So here we have the distance between the nuclei getting smaller and smaller, as you can see, right here, here. Now they're together, right? So the distance between them gets smaller, and the energy goes down. The energy gets lower. The y-axis here is energy, and it gets lower as they get closer together. Okay? So we can look at this in terms of the picture that we just saw, where far apart, they're just two undisturbed atoms doing their own thing. When they get close together, the attractions begin to pull them together a little bit, which is a somewhat lower energy configuration, and then eventually they get stuck together. The electrons are shared between them, and you have the lowest energy configuration, which is the hydrogen molecule, H2. So, thinking about this process and how this works, we can come up with some general rules that actually apply to the formation of a lot of covalent bonds and a lot of covalent molecules. So in a hydrogen atom, you have, again, one nuclei orbited by a single electron, whereas in the molecule, H2, you have two nuclei, and together they are orbited by two electrons. In the hydrogen atom, that electron is unpaired, right? A single electron is going to have either spin up or spin down, but it's going to be unpaired, and so the orbital that's in is incomplete. In the hydrogen molecule, the new orbital that's formed has two electrons in it, so they're paired, spin up and spin down. And that is a complete orbital, and since they orbit both nuclei, they sort of glue them together or hold them together, and so that actually constitutes the bond that holds the hydrogen atoms together in the molecule. In hydrogen atom, neither atom has a noble gas configuration, right? In a single hydrogen atom, you have a 1s orbital and it has a single electron in it. Okay? It's an unfilled orbital. In a hydrogen molecule, you do have sort of a noble gas configuration. Okay? It's not exactly a 1s orbital. It's sort of a new type of orbital that's formed from the combination of 1s orbitals. But whatever kind of orbital it is, it has two electrons in it now, one from each atom. And so whatever kind of orbital it is, any orbital can only hold a maximum of two. So this is a complete orbital, and it's actually a complete energy level, which gives it a noble gas configuration similar to helium. Okay, so this is again why hydrogen is stable as a molecule. So this picture is useful for small molecules like hydrogen and some other small ones, but it can get pretty complicated if you use more atoms or the atoms have more electrons. Okay, so instead of thinking in terms of these balls zipping around, we have Lewis symbols. Okay, and we learned about Lewis symbols back in chapter 4. You can consult video 4.8, slide 6, which shows you the Lewis symbols, and really you're just writing the symbol for the element and surrounding it by the number of valence electrons. So if you forget about valence electrons, go back and review that. It's essential for this process, for this topic. You have to know valence electrons. So for instance, boron is in group 3A or 13. It has 3 valence electrons. Carbon is in group 4A or 14. It has 4 valence electrons. Nitrogen has 5, oxygen has 6, fluorine has 7. The next element, which would be neon, has 8 valence electrons. We don't bother with that because it already has an octet. It's not going to form compounds, so we forget about the noble gases. Okay. So drawing the Lewis diagrams this way, when we first learned it, we were sort of particular about where to put the dots, right? It doesn't matter if the lone pair on nitrogen, for instance, is on top or on bottom, but you know you have one lone pair and 3 separate electrons, okay? In oxygen, you have 2 lone pairs and 2 individual electrons, and it's important to remember that. You don't want to draw oxygen as having 3 lone pairs, right? That's still 6 electrons, but the problem is it interferes with using these to create Lewis diagrams. Okay, so understanding how many unpaired electrons an atom has helps you understand how many bonds it forms. Okay, and so that's the idea. However many unpaired electrons there are in the Lewis symbol for an atom, that's how many bonds it tends to form. So boron tends to form 3 bonds. Carbon tends to form 4 bonds. Nitrogen tends to form 3 bonds, right? It doesn't bond here because that's a lone pair. It's already satisfied. Oxygen tends to form 2 bonds. Fluorine only forms a single bond. Hydrogen, which I didn't write, but hydrogen has a single electron. It's unpaired, and it forms 1 bond, as we saw. Okay? So understanding these Lewis diagrams and writing them properly with the correct valence electrons is very helpful for drawing molecular Lewis structures. Okay? And we're going to see that these single unpaired electrons tend to share with other atoms in such a way that all of the atoms involved get an octet. Okay, they satisfy the octet rule. So again, instead of drawing little pictures of protons and electrons as spheres and fitting them together that way, it's helpful to draw molecules with these Lewis symbols. So a molecule can be represented by a Lewis structure, in which the shared electrons or bonding pairs are shown as either two dots between an atom or a single line connecting the two atoms. And then the non-bonding pairs, or the lone pairs, are placed next to or on top of the atom that they belong to, that they came from. Okay? So to see an example of this, let's look at how we would draw the Lewis structure, or the Lewis diagram, or sometimes the electron dot symbol for ammonia, NH3. Okay? So the formula of ammonia tells us that we have one nitrogen and three hydrogens. Okay? And nitrogen has 5 valence electrons, one lone pair, and 3 unpaired electrons. And each of the 3 hydrogens has a single unpaired electron. So without thinking about it too much, it should be pretty clear how these pair together, right? Each unpaired electron wants to find an unpaired electron from another atom to connect to. And so that's what happens, right? We have unpaired electrons that are joining together to form bonding pairs, whereas the already paired lone pairs don't do that. Okay? So here, as the hydrogens approach the nitrogen, the unpaired electrons from the two different atoms join together. And so we get these 3 red pairs of electrons here, which are now bonding pairs. These are the covalent bonds between nitrogen and hydrogen. And we can represent covalent bonds as a straight line. Right? We just have to remember that that straight line, which is really a bond, is actually a pair of electrons holding those two atoms together. So take another example. We can draw the Lewis structure for fluorine gas. Okay, so fluorine, like hydrogen, is not stable as individual atoms, but when it pairs up, it can be stable. So 2 fluorine atoms can join together. Why is that? Well, if you look at the Lewis structure, or the Lewis symbol for fluorine, it has 7 valence electrons. That means each fluorine atom has an unpaired electron that's available to share. So if 2 fluorine atoms are near one another and they both have an electron that they want to share and they're both looking to get an electron from someone else, well, it's natural that they would join together. Okay? So the 2 unpaired electrons come to form a shared pair, which is a covalent bond. Okay? So by themselves, neither fluorine atom has an octet. But now that the shared pair, the covalent bond, is between them, each fluorine seems as though it has an octet. It's surrounded by 8 electrons. Okay? So there aren't actually 16 electrons in this molecule. There are only 14. Okay? Each fluorine has 7 valence electrons, and so the molecule is going to end up with 14 valence electrons. 7 plus 7 is 14. But even with 14 electrons, because 2 of them are shared, each fluorine can feel as though it has an octet. And again, we can replace the bonding pair with a straight line to indicate the bond, as long as we remember that that still counts as 2 electrons when we're counting up valence electrons. And so this is the Lewis structure for the molecule whose simple molecular formula is just F2. Okay? This is a fluorine molecule. This is a space-filling model of it here, which just shows a little bit how the atoms actually stick together, in a sense. So in addition to fluorine and hydrogen, there are 5 other common elements that form diatomic gases. Okay? So these elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All of these exist as diatomic molecules. Now, bromine and iodine, bromine is liquid at room temperature, iodine is solid at room temperature, but they both give off vapors that are diatomic gases. And if you heat them up a little bit, they go into a gas phase, which is a diatomic gas phase. Okay? But much more commonly, you're going to see hydrogen, nitrogen, oxygen, fluorine, and chlorine. Those are diatomic gases. So if you ever encounter a problem where they're talking about oxygen gas, that always means O2. Okay? It's not individual oxygen atoms. This table shows the valence electrons and bonding patterns of the nonmetals that we're going to be dealing with. Okay? Pretty much all of the covalent or molecular compounds that we're going to look at in this course are built up from this set of atoms that you see right here. Okay? So this is sort of an abbreviated periodic table. And what it does is it shows you how the number of valence electrons relates to the number of electrons that the atom needs to gain in order to achieve an octet, which in turn relates to the number of bonds that it likes to form. Okay, so for every electron that an atom shares, it also sort of gains an electron from the other atom sharing with it. Okay, so if an atom has, for instance, 4 unpaired electrons like carbon does, then each of those unpaired electrons gets shared, and in turn the carbon has 4 new electrons shared from other atoms. And so 4 plus 4 is 8, and that gives it an octet. So the number of unpaired electrons tells you how many bonds the atom likes to form. Carbon has 4 unpaired electrons, 4 valence electrons, they're all unpaired, and so it forms 4 bonds. Boron has 3 unpaired electrons, it forms 3 bonds. Hydrogen has 1, it forms 1 bond. Okay? Then they get a little bit more complicated because you have to think about how the lone pairs fit in. So nitrogen has 5 valence electrons, but remember it has 1 lone pair and then 3 unpaired electrons, and so it forms 3 bonds. Right? It wants to get 3 more electrons to get an octet, so it needs to find sort of 3 other atoms or make 3 bonds with 3 electrons donated from other atoms. Okay? Oxygen has 2 lone pairs and 2 unpaired electrons, right? So it forms 2 bonds from each of those unpaired electrons. Fluorine and all of the halogens really have 3 lone pairs and then a single unpaired electron, so they all form 1 single bond. So looking at this, we've already seen how we can construct a few simple Lewis structures, but in general there are really 2 methods for coming up with a Lewis structure. Either way should work, but some molecules it's easier to do it one way or another. So the first method we basically saw already, and that's that you just take the individual Lewis symbols for all of the atoms in the formula, and you just sort of try and fit them together, fit their unpaired electrons together like puzzle pieces. Okay? An unpaired electron from one atom can attach to an unpaired electron from another atom and form a bonding pair or a covalent bond. Okay? And if you can look at it and fit them together that way, that's one method that you can use. It takes a little bit of experience, a little bit of practice, but it can be very simple once you get the hang of it. Method 2 is a little bit more rigorous. It's sort of an algorithm where you step by step go through and you determine the arrangement of the atoms, how they're positioned relative to one another, how many total valence electrons there are in the molecule based on the individual atoms, and then you go through and you add electrons to it in such a way that you make sure that everything has an octet. Okay, so method 2 is more of an algorithm or a process that you can go through. It works for everything, but it's a little bit slower. Okay, so if you can get the hang of method 1, it's probably preferable, but method 2 should always work as well. And so we're going to take a look more at this second method. Okay, so this is the first method, just to remind you. Okay, we're drawing methane. So this is CH4, 1 carbon and 4 hydrogens. So if you look at the Lewis symbol for carbon, again, it has 4 unpaired electrons. Each hydrogen has 1 unpaired electron, so it shouldn't be too confusing to recognize that each of the unpaired electrons in carbon is going to pair up with one of the hydrogen atoms, one of the electrons from a hydrogen atom. And so what you're going to get is this structure, where the carbon is surrounded by 8 electrons, and each hydrogen has 2 electrons. Okay, so the carbon has an octet. Hydrogen has just 2 electrons, but that's fine because it's an exception to the octet rule. Okay, so you go from all unpaired electrons in the individual atoms to all paired electrons in the Lewis structure. Okay, this is a very important thing to notice. Pretty much every molecule that you're going to see in this course has only paired electrons. Okay, a molecule that has an unpaired electron is known as a radical, and it's very unstable. It's not something that we really study in this course. So every molecule, every polyatomic ion that you see has to have an even number of electrons, so all pairs of electrons. Okay. And so we can take this Lewis structure and we can represent it with these lines to indicate the bonds. And so this is typically what you would see written as the Lewis structure for methane. Okay, and again, because it's so simple, it's just hydrogens and carbon, it's easy to see how these pieces sort of fit together like a puzzle. The second method can be used for slightly more complicated molecules or things that might not be so clear when you first look at them. So let's use the second method to draw the Lewis structure for PCl3, phosphorus trichloride. Okay, this is used in the preparation of pesticides and flame retardants. So step one in this method is to count up the total number of valence electrons. So remember, electrons can't be created or destroyed, so all of the valence electrons that the atoms have going into the molecule are part of the valence electrons of the molecule itself. So phosphorus has 5 valence electrons, right? There's one phosphorus atom, so that gives you 5 valence electrons here. Chlorine has 7 valence electrons. It's in group 7A or 17. And there's 3 chlorine atoms in PCl3. Okay, so each chlorine atom has 7 electrons, so 3 times 7 gives you 21. So in total, the molecule itself has 26 valence electrons, 5 from the phosphorus and 21 from the chlorines. Okay? So when we draw our Lewis diagram, we need to make sure that we account for 26 electrons. Okay? Again, these are valence electrons, and I may leave out the term valence occasionally when I'm talking about these, but it should be understood that these are just valence electrons. These molecules and these atoms have more core electrons at lower energy levels, but those are not important for the chemistry, so we ignore those for the most part. Okay, so 26 valence electrons are in phosphorus trichloride. Step 2 is to determine the arrangement of the atoms. How are these atoms actually connected together, right? Before we worry about where all the dots go and where all the lines go, what is just the arrangement of the nuclei themselves, the atoms themselves? So in PCl3, there's just one phosphorus, and it typically forms 3 bonds. And there are 3 chlorines that typically form 1 bond. So it should be, again, pretty clear what the arrangement is. There are some rules that we'll see later on about how you can predict which atom is likely to be the central atom. For now, most of the time, the first atom, the first element in the formula is the central atom. So here P is first, and so P goes in the center, and the chlorines just sort of get placed around it. Step 3 is to begin to fill in the bonds between the atoms. And most of the molecules that we're going to deal with, you have a central atom, and then all of the other atoms are bonded to that central atom. There'll be some a little bit more complicated ones later on, but that's the main way that these molecules are going to be structured. Okay? So in this case, we have phosphorus in the center and chlorine on the outside, so each chlorine has to be attached to the phosphorus. So we can draw a bond from the chlorine to the phosphorus. And once we've drawn a bond for each of them, we've now accounted for 6 electrons, right? 3 bonds. Each bond is 2 electrons. 3 times 2 gives you 6 electrons. Okay? That's out of the 26 total. Okay? So if we have 26 total and we've already drawn 6 of them, we have 20 electrons left to put into this molecule. Step 4 is to just sort of place them as electrons to complete octets. So first you would want to complete the octet on phosphorus, right? It has 6, 2 here, 2 here, and 2 here, and so we want to give it 2 more to give it an octet. So you place that lone pair on phosphorus. That leaves you with 18, right? We had 20 after the first step, now we place 2 of those, and so we have 18 left. 18 electrons divided by 3 atoms is going to give you 6 electrons per atom. So each of these chlorine atoms gets 6 electrons, which is really 3 pairs, right? You should always be thinking about electrons coming in pairs for a Lewis structure. So each of these chlorines has 3 lone pairs. Okay? And then we can double check at this point and make sure that we have the right number, okay? So that we have all 26 electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 from the lone pairs. And then this bond is 2, 22. This is another 2, that's 24. And this is another 2 for the last bond, and that is 26 electrons. So we've accounted for all 26 electrons that we know are in the valence of this molecule. The last step that we have to do is make sure that all of the atoms have an octet. Okay? In this case, everything already does, so we're actually already done in this case. So phosphorus has these 2, and then 2 from this bond, and 2 from this bond, and 2 from this bond. That gives it 4, right? The chlorines each have 2, 4, 6 of their own from their own 3 lone pairs, and then again they share that bond, so they get 2 from the bond as well, and that gives them 8. Okay? So each of the chlorines has 8 valence electrons as well. So all of the atoms here have an octet, which means this molecule is done. Once you have all of the electrons placed and all of the atoms have an octet, or you know that there's some exception to the octet rule, then you know you're pretty much done with the molecule. Okay? You don't have to worry about moving anything around. If some of the atoms didn't have an octet, then you would need to think about moving the electrons around. Okay? If there are too many electrons in one atom, then you take some off and put them elsewhere. If there are too few electrons on an atom for it to have an octet, then you may need to start sharing more electrons with other atoms, meaning turn a single bond into a double bond or a triple bond. We'll see a little bit more about that later on. So there are ways that you can move the electrons around to make sure that you have octets everywhere. But the key is that every atom must have an octet. It's a very important step. So again, those are the steps that you go through, but there's still a little bit of art involved. There's a little bit of experience that you need to have to figure out some of these steps. So one of the main questions that students often have is how do you determine which is the central atom in a Lewis diagram? Okay, and so there are a few rules that you can use for this. Some of them are more rigorous rules. Some of them are just sort of general guidelines. So one of the most important rules is that hydrogens and halogens, the halogens meaning the group 7 elements, fluorine, chlorine, bromine, and iodine, the hydrogens and the halogens are always on the outside. Okay? And that's because they only form single bonds. Hydrogen can only form a single bond. It'll never form more than one single bond. Fluorine, chlorine, bromine, and iodine, they all have one unpaired electron, and they all form single bonds. They have those lone pairs, but they're only forming a single bond. Okay? In some texts, you'll see that chlorine and bromine and iodine can form double bonds through d electrons, but that's not something that we really need to worry about in this course. For our purposes, halogens are always going to form single bonds. Okay? The next rule, the next guideline, right? If you don't have any hydrogens or halogens, that first rule won't really help you. So the next rule is that usually the first element in the formula is the central atom. Okay? And this is a very good rule. It's almost always the case that the first element in the formula goes in the center. Okay? In fact, one of the only exceptions to that is just some formulas begin with hydrogen. Okay? So you'll have certain acids or things like that that begin with hydrogen atoms, but we already know that hydrogen can't be in the center. It's got to be on the outside. So if it begins with hydrogen, just look for the next element after the hydrogen, and that is going to be the central atom. Okay, so you can see that at play in each of these examples over here on the right. Okay, CH4, carbon is first, carbon's in the middle. NH3, nitrogen's first, nitrogen's in the middle. And this is that exception where hydrogen is first, right? In this case, hydrogen is first, but since hydrogen can never be in the middle, oxygen must be in the middle, and the hydrogens are on the outside. Okay. The next sort of guideline is that the central atom is usually the one that forms the most bonds. Okay, and that's just by nature of how these molecules form. The central atom is going to tend to form the bigger number of bonds. So with CH4, for instance, the hydrogens only form a single bond, whereas the carbon can form 4 bonds. So the carbon goes in the middle. Nitrogen can form 3 bonds as opposed to hydrogen's 1, so nitrogen goes in the middle. Oxygen can form 2 bonds, whereas hydrogen can only form 1, so oxygen goes in the middle. Okay, that's another pretty good guideline. Another thing to think about is that usually Lewis structures are symmetrical. Okay? So if you have a single atom and then several of another type of atom, the single atom is probably in the center with the other atoms symmetrically distributed around. Okay? Usually that's the case, not always, but it's usually helpful. And then another rule that you see is not really a rule, but some textbooks mention this. You'll see it online a lot, where the least electronegative atom is the central atom. I'm not sure that's really a hard and fast rule. I think it mostly comes from the fact that more electronegative atoms tend to form fewer bonds, right? The halogens are some of the most electronegative elements, and they all form single bonds, so they're going to tend to be on the outside. So I think this is really just a consequence of some of the other rules, but I just wanted to mention it because you do see it written in some places. But it's not really the most helpful. We haven't even really talked too much about electronegativity yet. I've mentioned it a couple times, but we'll get more into that later on. So here we can see what happens in that last step if you find that you've placed all of your electrons, but you don't really have octets around everything yet. This is the case where you might need to start thinking about double and triple bonds. Okay? So to give an example, if we have CO2, right? Well, based on what we just said, C should be in the middle and O should be on the ends for a couple of reasons, right? C is first in the formula. C forms more bonds than oxygen does, and this is the more symmetrical arrangement. So for all those reasons, this is likely to be the way that CO2 is laid out. Okay. For CO2, we know we have 4 electrons from the carbon and 6 from each of the oxygens. So 6 plus 6 is 12, plus 4 is 16 valence electrons. Okay? So CO2 has 16 valence electrons. So if we begin, we can put single bonds between each carbon and each oxygen, right? That's 2, 4. And then we can start adding our electrons as lone pairs. So 2, 4 from the bonds, 6, 8, 10, 12, 14, 16. And then we're out of electrons. We can't add any more dots to this diagram because there are no more electrons in this molecule. And if you look at this molecule, there's some things wrong with it. Okay? So the left oxygen and the carbon both have octets, so that's okay. But the right oxygen does not have an octet. It looks like it only has 4 electrons, which is certainly not an octet. Another thing to notice is that usually oxygen forms 2 bonds and carbon forms 4. But in this case, both oxygens are only forming 1 bond and the carbon is forming only 2. So that's another reason why this is not really the best diagram. Okay. So, and then a last thing is that it's not really symmetric. The way that we place the electrons sort of destroyed the symmetry. So the first thing you would want to do is try and make it a little bit more symmetrical. So I'm going to remove one of the lone pairs from this oxygen and put it over here, right? So that we're not gaining or losing electrons, but now the molecule looks a little more symmetrical again, okay? And the problem there is that that kind of destroyed one of our octets, and it didn't quite give us an octet on the other one. So now we have to think about how we can shuffle these electrons around to share more. Okay? And so the way that you should think about this is carbon has an octet, so that's fine, but the oxygens have too few electrons. So each oxygen has only 6 electrons. So if an oxygen has 6 electrons and it needs 8, that means it needs to share 2 more electrons. So to do that, you can take the single bond and turn it into a double bond, but you need 2 electrons to do that. So you have to take these 2 electrons and put them here as a new bond. Okay? So by doing that, you get rid of these electrons up here, and this becomes a double bond. And a double bond is 4 electrons, right? Single bond is 2, double bond is 4. It makes sense. And so now you can see that we've actually fixed this oxygen. This oxygen has 2 electrons here, 2 electrons here, and then 4 from the double bond. So that is a total of 8 electrons. So this left oxygen now has an octet. The carbon still has an octet because the 2 electrons which were on just the carbon are now part of a bond that's still going to the carbon. So it still gets to count those. Okay? And then we can see that the other oxygen, which is also lacking in electrons, we just need to do the same thing. We need to take this bottom lone pair and turn it into a double bond. So I can just erase the lone pair and put a double bond there. And so this is the Lewis structure that we end up with, right? It looks basically like this. They just put their electrons in a slightly different place. But so this is how we get the Lewis structure where even though it seems like we don't have enough electrons, we can share them in such a way that each atom feels as though it has an octet. Okay. You can do the same thing with a triple bond. So you can look at this HCN cyanide molecule if you want to try an example, and you can see how that works, right? Nitrogen tends to form 3 bonds, so you can end up with a triple bond to the carbon. A lot of this has been predicated on the octet rule. We've talked about how atoms want to satisfy the octet rule, how you can shuffle electrons around in a Lewis diagram so that everything has an octet around it. And the octet rule is incredibly useful, but there are exceptions, okay? We've already seen a couple, right? So hydrogen is a very, very common exception to the octet rule. Hydrogen only needs 2 electrons to be stable because it's in the n=1 energy level. It really doesn't need electrons in its higher energy level. So hydrogen is stable with just a single bond, which is 2 electrons. Okay, you can call that a duet. Beryllium is another exception. Beryllium requires just 4 electrons. Beryllium has 2 valence electrons. Okay, so it has 2 unpaired valence electrons, so it can form 2 bonds, which is 4 electrons, and so it can be stable that way. One thing to notice about beryllium is it's not really a nonmetal. Technically, beryllium is a metal, but because of its high ionization energy, because it's so small, it does typically form covalent bonds. So you'll see it sometimes in questions and chapters and textbooks about covalent bonds. Okay, so beryllium is an exception where it just forms 2 bonds to get 4 electrons. Okay? And then the next exception, which we've seen before, is boron, which has only 3 valence electrons, right? And so it can form 3 bonds from those, and that gives it 6, and it's satisfied with 6 valence electrons. And so you'll often see a diagram of a boron molecule like this, okay, which is the same thing down here. Okay, boron in the center, chlorine on the 3 corners, and it has only 6 electrons around it. So it does not have a full octet, but that's fine. It's satisfied that way. So those 3 examples are where atoms may have less than an octet. But for elements in period 3 or greater, right, that's the 3rd row of the periodic table, and down, those elements have d orbitals that are available, and available in the sense of they have energies that are accessible in typical chemical reactions. And so these elements can actually have what are called expanded octets. They can sometimes have more than 8 electrons around them. Okay? And so this includes phosphorus, sulfur, chlorine, bromine, and iodine. For chlorine, bromine, and iodine, you're not really going to see this that much. So again, don't worry too much about that. But for phosphorus and sulfur, you may see expanded octets. Sulfur especially is a common example. Here's one example of sulfur, SF6, where the central sulfur is connected to 6 fluorine atoms, right? So it has 6 bonds. 2 electrons each gives you a total of 12 electrons in the SF6, or surrounding the sulfur in SF6. And it can do that, again, because those electrons are able to go into the d orbitals that begin to be accessible from period 3 and higher. Let's do a couple more examples of using the second method to draw a Lewis diagram using that step-by-step process. Okay, so here we want to draw the Lewis structures for SCl2 and SO2. That's sulfur dichloride and sulfur dioxide, 2 sulfur compounds. Okay, so they look similar at first. You have sulfur connected to 2 other atoms, but we're going to see that they're a little bit different and why that is. Okay, so the first thing that we should do, remember step 1 of this method, is to count up the valence electrons. So sulfur has 6 valence electrons. Chlorine has 7 valence electrons. But in SCl2, there's 2 chlorines, so we have to multiply that 7 by 2 to get 14. Oops, to get 14 valence electrons. Okay? 6 plus 14 gives you a total of 20 valence electrons. Okay? So SCl2, we need to place 20 valence electrons in the Lewis diagram. For SO2, we have, again, 6 electrons for sulfur, and then the oxygens are also 6. They're all both in group 6, so oxygen, there's 2 of those, though, so we need to multiply that by 2 to get 12, right? And then 6 plus 12 gives us 18 electrons. So we can already see that there is a slight difference in these 2 molecules in terms of how many electrons are in them. So SCl2, sulfur dichloride, has 20 valence electrons. Sulfur dioxide has 18 valence electrons. Okay? So now that we know that, we can start thinking about the arrangements of the atoms in these molecules. And these are not too complicated, so the rules that we have are sufficient. So for SCl2, the first element, S, is in the center, and then the Cl's are on either side. Same thing with SO2, S is in the center, the oxygens are on either side. Okay? Again, this follows the pattern of the first element being in the center, the element that forms more bonds being in the center, although in the case of SO2, that's not quite true. They both tend to form 2 bonds, but we'll see why that's a little bit different actually. But also the least electronegative element is in the center. So all these things, again, lead us to this arrangement. They're also both symmetrical. Okay? You have the 1 atom in the middle, and then the 2 atoms on either side. Okay? So now that we have what we think is probably the arrangement of atoms, we can start putting in the electrons. So you start with just a single bond to the central atom, okay, for all these, just a single bond. So that accounts for 4 electrons in each of these, okay, right? So we started with 20 electrons here and 18 electrons here. So after putting those 4 in, we're down to 16 here, oops, and 14 here, okay? So then the next thing that we can do is really just sort of put in the rest of the electrons. We don't want to think about double or triple bonds yet, so we're just going to think about adding the electrons in, the rest of the electrons. And we do that starting with the central atom and then going to the outside. So we're going to add 2 electrons, or excuse me, 2 pairs to sulfur to make that 8. Right, so that's going to be minus another 4, which gives us 12 left. We have 2 atoms that we want to add electrons to, and 12 electrons means each of them gets 6, or 3 pairs. Again, always think of electrons in pairs. Right, 2, 4, 6, 2, 4, 6, that gives us 12, and so now we're out of electrons. We're down to 0. Right, again, 2, 4, 6, 8 on the chlorine, 2, 4, 6, 8 on the other chlorine, then another 2, 4. So that gives us 20 electrons in total are in this molecule. Okay. Going to sulfur dioxide for a second, we have 14 left. So again, we'll start with those 4 on the central sulfur, which leaves us with 10. But then we run into a problem because we have 2 oxygens left and only 10 electrons. So if we split them evenly between the 2 oxygens, then the oxygens are going to get an odd number of electrons, right? We could put 2, 4, 2, 4, that would give us 8, and then 9 and 10. But you should never ever have unpaired electrons in a Lewis diagram. So we would want to get rid of those and put them as a pair somewhere. Well, where do we put them? Well, we could put them on either oxygen. We could put them on this one or on the other one. The problem with this is that if we put them here, that gives this oxygen an octet, but the left oxygen is left without an octet. Okay, so I'm going to come back to that in a second, but let's just look at SCl2 and make sure that that's correct. So this chlorine has 3 lone pairs, that's 6, and a bond for another 2, that's 8. This chlorine has the exact same pattern, so that's also 8. This sulfur has 2 lone pairs for 4 and 2 bonds for another 4, and that gives it 8. So all of these atoms have octets, and so this SCl2 molecule is done. It looks like a good Lewis structure. So we can say that this is the Lewis structure, the Lewis diagram for SCl2. Okay? But we already see how it's not quite so simple for SO2. So now we have to think about what we can do, right? I just sort of arbitrarily placed this last lone pair onto this oxygen to give it an octet, but we still have this other oxygen that doesn't have an octet. So there's a couple of things that we can do about this, okay? We can first take this lone pair and turn it into a double bond here, okay? So just by moving these 2 electrons to here, we turn this into a double bond, and now it looks like we might actually be done. Okay, let me erase this to give myself a little more room because I'm going to want to draw a couple of other things. But now we look like we're almost done. So this oxygen has 4 electrons from its lone pairs and another 4 from the double bond, so that gives it 8, an octet. This oxygen, we gave an octet by just sort of randomly giving it those last 2 electrons that we needed to place. So it has 6 from its lone pairs, another 2 from the bond, and that gives it 8. This central sulfur has 2 electrons from the lone pair and 6 from the 3 bonds that it shares. So 6 plus 2 is 8. So this is good. This is an okay Lewis structure. Okay? The problem with this is that it's sort of arbitrary, right? I chose to put the electrons on this oxygen rather than the other oxygen for no real reason, just because I picked it. So we could easily have taken it and done it the other way and put that extra pair on the left oxygen and then had the double bond going to the right oxygen. And we would end up with something like this, right? Or we could also recognize that sulfur can sometimes have what's called an expanded octet, and we could say that sulfur could form two bonds to both oxygens, right? And then each oxygen would have two lone pairs, right? Basically what we're doing is taking this lone pair and turning it into a double bond here, right? And so this has the advantage of being symmetric, even though sulfur now has an expanded octet. It has 8 from the bonds and then an extra 2 for 10 electrons. But that's okay for sulfur. Okay? So this is a little tricky to understand at first, because we naturally sort of want to know which of these is the right answer. And the real answer is that all of them are correct. Okay? The actual SO2 molecule is sort of an average of all three of these structures. Okay? None of these individual structures completely describes the SO2 molecule fully correctly. The real molecule has aspects of each three of them sort of together. Okay? And so these are what we call resonance structures. Okay? Resonance is not something that we're really going to study too much in this class, but it is good to know that when you're drawing Lewis diagrams, there are sometimes multiple ways that you can draw an accurate Lewis diagram. And if that's the case, then often those different ways will be resonance structures. They'll both contribute to the true structure of the molecule, right? Remember, we're just drawing little lines and dots on pieces of paper, so there's no reason that we should really be able to represent all of the properties of a molecule with such a simple notation, right? It's pretty miraculous that we can get anywhere near the reliability that we have. So this is one way that we can improve that by recognizing that there are sometimes multiple ways, multiple different arrangements that sort of contribute to the real arrangement. Again, this is all predicated on sulfur having an expanded octet, or recognizing that Lewis diagrams tend to be symmetrical.